want to start, actually, because I think there's probably one thing that most people want to know, which has been asked of almost every astronomer in the last 24 hours. So many of us stayed up last night, getting technical instructions. So many of us stayed up late last night to see the briefing, to see that very first image introduced by President Biden. And just how did you feel when you first saw it? Perhaps someone could start expressing that. And what do you think, if this is your area of study, what do you expect it to tell us when the real work starts?
So I was in my hotel room last night, waiting for a long time, listening to some elevator music for about an hour on loop, just getting more and more apprehensive and kind of scared, excited, because this image that we saw last night is one of the ones that I'd be interested in. This is going to give us our first view of the distant universe. So in this image, we can see galaxies stretching back across almost the entire history of the universe. And we're really interested in actually looking at some of those galaxies and figure out where they've happened. So as soon as we had that image, we downloaded it, and we were trying to do science on this publicity lit image and trying to work out, oh, that galaxy looks really cool, what can we do with it? But this is really, really just the tip of the iceberg. And I think we're going to hear that a lot today. These are the first 5 promotional images that we're going to get. We're going to be able to do science with these images, but there's going to be hundreds, thousands of times more data coming out over the next weeks, months, and even decades where this is going that well.
Yeah, and I want to highlight that you've got this beautiful image that came out last night behind us. And not only have you got these amazing galaxies in the background, but you've also got these really bright stars in the foreground. And those bright stars have these really distinct spikes on them. Those spikes are caused by the fact that this telescope is made up of a series of 18 hexagons. So if you piece them all together, this is what it does to the light, and they're called diffraction spikes. And those spikes really, really tell you that this is a complicated instrument. It's really, really fascinating look at how it deals with the light. But look how crisp it is. And that is really the key to JWST. We're getting these really crisp, clear images from it. And from that, we can do even more exceptional science.
Yeah, and just to add to that, I think, well, we've all been sort of growing up looking at amazing Hubble images, and we thought, it couldn't get any better than, deep Hubble imaging. And then yesterday, this came out for 12 hours, and suddenly we see so much more detail. It's just incredibly, well, I don't want to say sharper because I'm not really sure exactly how that would end up, but in terms of sensitivity, it's just absolutely mind-blowing. And to think of this as one of the first images to be released, so it's not even one of the very ultra deep fields that has been collected over several days at once even, but just one of these deep images to be released very quickly. I can't even begin to imagine what a proper ultra deep image from web will actually look like. So yeah, it's just, it only gets better and better from there, I think, from a scientific point of view.
Most of you are fairly early in your careers, and so what do you think? We've had 30 years of Hubble. What are the longevity of where it's slightly different, but do you expect this to be game-changing in the same way that Hubble was? Are you looking forward to decades of analysis at this stage in the same way that it's happened? Do you want to go on this one? I'm just thinking it's the first one. So.
Yeah, I guess I do agree. But so the thing is, like a Hubble as well, that Hubble was not designed to do exoplanet science. As scientists, this is what I'm looking for, right? But JWST, we actually have increased in the exoplanet scientists this time, so we expect them to get way more out of it. To actually help design instruments and areas of science goal behind it, covering exoplanets. So as a PhD student, and all in the next couple of years, there's so many observations. We're going to learn so much, and we're so prepared for it. Well, we weren't prepared for Hubble at all, really. So I'm just super excited. Yeah, I'm looking forward to that.
One of the amazing things about this telescope is it was built and it's been managed by over 1,200 scientists from across 14 different countries, and the UK has a huge part in that as well. And because of all that beautiful engineering and precision and design and the time that they took to build it, we have 20 years of this telescope to play with. We were supposed to have 5. So this really is a career maker, and it is something that I intend to be working on for the rest of my career. And even when a telescope stops working, we know from previous missions and from various other things that have been going on, there's still so much data to play with. So I don't see this journey ending anytime soon at all. I think some people not born yet are going to be working on brand new data from this telescope, and that's really exciting.
So, I mean, actually, that's a nice segue, really, because the next release in the was about the exoplanet was 96B. These catalog names at the moment, so we get out, I guess, and start to find out I thought there's so many ones that's not going to be. I was thinking too that when Hubble was launched, we didn't know about any extrasolar planets. It was a couple of years later before they came along. So I think that's partly why it's been so great to be able to prepare for it this time. So that spectrum is of a world that's about half the magnitude racing around its star every 3.5 days. So very unlike anything we see in our solar system. And the telescope disperses the light passing through its atmosphere into a spectrum. So I just wonder if one of two of you perhaps could say exactly what that means, what a spectrum is, and what we can understand from it. Should we go that one now?
So I guess we first have to start with the spectrum is not actually directly image spectrum, it's actually transmission spectrum. So the hot tube memory was 96B, transits in front of the star goes in front of it, and we capture this transit. And what we then do is just split the light up in all different wavelength ranges, and that's the spectrum. We split it up, but then we look at the spectrum and see how different the absorption is, so how the transit depth of exoplanet going from the star varies across the whole wavelength range. So it's not directly the spectrum, it's kind of like, we get the transit depth per wavelength. That's what we're looking at here. And yeah, so we see water, which is a good start, especially because it has been confirmed with Hubble before that there's water in the atmosphere, and it's really nice to see that we're not wrong. This is a good start.
I'm guessing though, this isn't, maybe Hannah wants to take this, this isn't water that's going to be conducive to life on a world like this, but then the big question is, well, why is that the case? But also then the big question is, with James Webb, how much closer do we get to answering that question? You know, are there other Earth-like planets out there? What are the prospects for life elsewhere in the universe?
Yeah, and that's one of the important questions. What we're looking at here from this first spectrum that's come out is a hot Jupiter, like Evie said. And that means the atmosphere is incredibly irradiated by a star. Its year is 3 days or so. So this space is not somewhere you want to go on vacation. It's also Jupiter size, so it's mainly hydrogen and helium. It's over 11 times the radius of the Earth. It's a huge planet. So this water is in the form of steam, in the form of gas in the atmosphere, and it's fully mixed throughout that atmosphere. As we see with other planets in our solar system, water is a very common molecule across the entire universe. So we expect it to be there, and it's amazing that we've been able to measure it in so many different wavelengths, so different bands, as well as bumps, the individual bumps that you're seeing there. Those are each individual confirmation that what we're seeing is water vapor in the atmosphere of this planet. And what JWST is going to allow us to do is to push down to smaller worlds, to colder worlds, towards terrestrial rocky worlds that are perhaps temperate. So something that is maybe a little bit hot still, some a little bit cold, but you know, that temperature that is potentially just right. And the aim of this telescope is first and foremost to discover if those worlds have an atmosphere at all. So the first investigations we're going to be doing of these really small rocky worlds is going, does it have an atmosphere? Can we measure those absorption signatures that we're seeing there? So over the next couple of years, I'm sure we're going to be starting to see that, yeah, there are atmospheres around some of these. Let's try and learn a little bit more about them.
So I think we have a question on Zoom.
We had a request, if you could quickly reintroduce yourselves again, please.
Of course, yeah. So, well, I'm Robert Massey from the Astronomical Society. Do you want to pass the mic along from Maybe it's easier if it goes all the way up to the actual.
Hi, my name is Aayush Saxena, postdoctoral research fellow at UCL, studying galaxies.
My name is Nathan Adams. I'm a postdoctoral research fellow at the University of Manchester, and also similarly studying the most distant galaxies.
I'm Stephen Wilkins, the head of astronomy at the University of Sussex, and surprise, surprise, I also study distant galaxies.
So there's a theme.
Hi everybody, I'm Hannah Wakeford. I'm a lecturer in astrophysics at the University of Bristol, and I study exoplanet atmospheres.
I'm Eva-Maria Ahrer. I'm from the University of Warwick, a PhD student, and also do exoplanet atmospheres.
Thank you, everybody. And as you can see, so we have a panel of very talented astronomers here, mostly, I would say, close to the beginning rather than the end of their careers, which is fantastic. It's really nice to have people who are going to be able to explore this telescope to the full. So we were talking about extrasolar planets, and I guess also I do want to come back to, because we look at things like data or spectra, and you get, I think you described it about bumps and wiggles on a graph. And yet that actually is one of the tools of astronomy for everybody here, I think. So perhaps we understand we're looking for those bumps or those water vapor, which was shown so nicely in the briefing earlier. But what about for extragalactic work? What about those distant galaxies? By the way, you might want to state just how distant galaxies you're talking about, because let's face it, for all of us, galaxies are not exactly in our neighbourhood, although some have the title of being local.
Exactly. Yeah. Some of you may have seen earlier when they first started the live stream today. Well, yesterday they released this image that's behind us of this galaxy cluster. And amongst all of these objects in this galaxy cluster and the things that us as researchers after the most distant galaxies are interested in, we're after very tiny red blobs that you see around the periphery of the image. And what was announced today, which was a surprise I think to all of us, was that Webb has already gone and taken some spectra of some of those tiny red blobs. And these spectra revealed these to be galaxies at distances close to 1, sorry. So I was saying that Webb has taken some spectra of these tiny red blobs around the periphery of this cluster and has shown them to be galaxies at distance around about 13.1 billion years, which is going back to when the universe was only a couple percent of its current age. So what we're seeing is galaxies that are really at the early stages of their lifetimes. And so that's one of the things we're interested in scientifically, is trying to understand how the galaxies first come to be, how they form, where the structure, like spiral arms, things all come from. And yeah, so this is going to be a big surprise to us. And they showed one, but it actually seems like they've done 3 or 4 of them from what I've heard just before walking in here. So this has got everyone really excited. Yeah, 13.1 billion years is the figure that's been quoted at the minute.
so I've been asked by people, they'll say, well, okay, so you're looking back towards the beginning of the universe, and that time travel is a fantastic thing to think about. And then the next question that comes up was just how far back can we go? What are the barriers to looking back? What is the ultimate limit? What any telescope actually can do?
So that's a really interesting question, and one that's not very easy to answer, because the problem is, as we go back further and further and further, we're getting galaxies which are smaller and smaller and smaller and greater and greater and greater. So they're becoming more and more difficult. Before we had Webb, we were also really limited by the fact that we couldn't explore the infrared far enough. So as we look further back into the universe's history, the light from galaxies gets shifted into the infrared. And with Hubble, that really limited you to about a redshift of 10, which is about 500 million years after the Big Bang. But with Webb, in principle, you could push all the way back to the very first 1,000 galaxies to form the universe. The problem is, we just don't think there are that many of them. So we don't know exactly when we're going to be able to push to. But going back to the spectroscopy, because in the past, certainly for high redshift galaxies, we were only really using spectroscopy to confirm to us exactly when these galaxies were. But I think one of the big changes for our field is that we're going to be able to use spectroscopy to really, really probe the details of these distant galaxies. And the thing that I think that we're kind of most excited about, hopefully you two agree with me, is this idea that we'll be able to measure what these galaxies contain. So actually tell you how much oxygen, how much iron, how much nitrogen. And that's really important because all of these, what we call heavy elements, or what astronomers call heavy elements, they were not always around. So the Big Bang left us with just hydrogen and helium. and all those other heavy elements, which are vital for our own existence and for the planets that Hannah's going to study, they had to be made. And they were made while stars lived and died. And so it's always been a little bit of a mystery about how this process evolves and changes over time. But with Webb, with its spectroscopic capabilities and its ability to find these galaxies, we'll be able to actually, watch the buildup of these heavy elements, which are so vital for our own existence over time. And I think that's going to be, the real great thing about spectroscopy. So I think the image that we just saw about half an hour ago, that was, a big surprise to us that, they've already made some of these measurements. They're already seeing galaxies at these, distances which have oxygen and nitrogen in them. And I can't wait to look at the data.
Thank you. Now, looking a bit closer to home, some of the other images have actually been of stars at different points or associated with stars. And one of them was the so-called Southern Ring Nebula. So, like the Ring Nebula is a famous astronomical type of nebula. Northern hemisphere, the southern ones in the southern hemisphere. And that's an image of a star at the end of its life. And it looks like a beautiful ring, as the name implies. So, I think it's been a Hubble target as well. So, is this as an example demonstrating what is it that exactly JWST can show us that Hubble can't, systems like that. Why is that the case? What is the big advantage of using this telescope? It's such a fabulously complicated project to get into space and get it on the ground. Why would we use it rather than using telescopes on the ground?
Yeah, that's an important question, isn't it? Like we've looked at these targets before, so what are we learning that's new? And it comes back to what Stephen was saying about that infrared light and the ability to see different aspects. With these ring nebulae, for example, the main thing that we can do with JWST is we can peer through the dust that was obscuring the view from Hubble. So when you see these ring nebulae, there's a central point of light, and then you just got this really bright reflection of that light from dust that has been expelled from this dead star. So this star dies and it ejects all of its atmosphere. It blows it away. So you create this bubble in space, essentially. And at the edge of that bubble, you're seeing the lit up parts of its old atmosphere. But those parts are made of material that is opaque in the optical, so you can't see through it. It looks like a solid material. But if you look in the infrared, you can see right through it to what's happening in space behind it. And what JWST has revealed from this beautiful nebula is this cavity, this three-dimensional structure that is behind all of that material. The motes of different clumps of dust and gas that is slowly coming together and being forced together by radiation pressure. And we can start to see that there's actually other stars there in the background. We can see further into the universe behind these obscuring objects. So it's this remarkable ability to not only see new things, but see at what point we can start seeing through things, because that tells us something about the properties of that material. So it tells us about the size of the material, and that alone can tell us a huge amount about the dynamics and the pressure and the physics that had to go into this exploding star to create this structure.
And there's also, I think, another one, which is in this box of gifts for astronomers that you've got today, which is a stellar nursery, the constellation Carina. So get down to the southern hemisphere, that's basically a giant cloud of gas and dust that puts newborn stars. And again, we're very used to those Hubble images of settings like that. But what is it that I know not you necessarily work on forming star systems, but what are the kind of science goals there? What do people want to use James to understand?
Yeah.
Yeah, so I think the process of star formation in the universe, within our own galaxy or in galaxies that are very far away or even nearby, is very, very complex, right? And with Hubble, we could only see the stars that are actively being formed, that emit the ultraviolet and optical wavelengths that Hubble can see. But we know now that a lot of the star formation that happens in the universe is actually obscured by dust. So if you don't have access to the infrared wavelengths, you have no idea how many stars are forming in regions where you can't directly peer into with things like Hubble. And there are estimates of the majority of star formation in the universe may actually be obscured by dust. So if you count all of the star forming regions within our own galaxy or galaxies across cosmic time, we may be missing a large stellar mass that is forming behind these dust obscured star forming regions. And this is very important to really understand the buildup of stars across the universe. And with Webb, we can actually, for the first time, look at these obscure star forming regions, both within our own galaxy and galaxies across cosmic time as well, which will give us a very strong sort of constraint on how many stars are actually forming at any given time, at any given place in the universe, which is very, very important to understand, say, the evolution of galaxies across time, but also how stars form within our own Milky Way. So I think without Webb and without access to the infrared wavelengths, we will never be able to really see this dust obscured star formation, which we can now. It's very exciting. This is, I think, what we saw in the birth of stars image that NASA showed.
I mean, that brings up almost a philosophical question in my mind, which is, we know that the universe has changed over time, so if we go back in time, there were periods when more stars were forming, and I don't know, maybe we describe the universe as being in its middle age at the moment. And what are the prospects going forward? You know, I know not necessarily cosmologists, but as you run forward, there's less fuel available for making new stars. You know, is Webb going to give some insight not only into the way the universe began, but also the way it might end? Does anybody want to put their neck out on this one? Let's just make that one, Stephen.
So I spent the early part of my career actually, more holistically looking at star formation across the entire history of the universe. And I used to give a lot of talks about this, but the reality is that actually every year that passes now in our universe, the amount of new stars being born is actually going down all the time. And that's for a couple of different reasons. So first of all, our universe is expanding, so some stuff is getting further away from other stuff. We're using up some of the fuel of the universe, we're already converting it into stars. But then the stars and supermassive black holes that are there, they also tend to heat up the remaining gas in a process called feedback. So it's a little bit depressing actually that our universe, as we go forward, it does appear to be, kind of, I don't want to say dying, but it's certainly into the middle age now, just like myself. It's definitely middle age. And although that's weird, and we can maybe extrapolate into the future, I think that's a dangerous thing to do in astronomy. I think, the cosmologists will try and tell you what's going to happen in the future. So you talk about things like a big crunch or a big rip or the heat death of the universe. But the reality is, every time we look at the universe in a new way, we discover, something almost entirely unexpected. So there's really good history in cosmology of this. Things like dark matter and dark energy, which completely changed how we think the universe is going to change over time. And it may well be, although Webb isn't designed to really answer some of these cosmology questions, that Webb might find something else that might provide a new insight into some of those mysteries that change what we think is going to happen in the future of the universe.
I mean, it's a fair point, which is, I think, that it's an unusual space mission or a new telescope. It doesn't change some of our ideas. There aren't these little random shifts going on, some of those very big shifts. But you talked about the fact that the number of stars being born every year is declining over time. At what point should we worry about existential crisis?
A long time in the future. It shouldn't keep you up at night.
That's a suitably vague astronomical answer. Thank you. I mean, also in the list, we've actually going back to your field, we've got an image of another galaxy cluster, which is well, you might consider to be close. I think 290 million light years away. Stephan's quintet, which is, I think, a target for some amateur astronomers who like the fact that there's 5 galaxies together, and they're not easy things to see, but you get fantastic people doing astrophotography to pick them out. So that's another great image, and what is it that new that JWST is telling us about those galaxies?
So while we were briefly discussing the exoplanets, that you may have noticed the 3 of us over on this side were crowded around the laptop at that moment. But that was the moment that the second image was being released, and we were both going, ooh, wow, over it. But definitely, I think the first thing that leapt out to us looking at this new image was the amount of structure there is around the outside of these galaxies. indicating that there are some interactions between them going on. So there's 5 galaxies that make this up. I believe 4 of them are close enough to each other that their gravities are pushing and pulling on each other. And one of them just conveniently looks like it's nearby, but it's actually quite far behind them. But we're seeing some weird, what we would call tidal structures, or these like large streams coming off of these galaxies that are showing that as they're passing by each other or interacting with each other, they're throwing gas and dust and things outside. And so this is really interesting in regards to how galaxies evolve in dense environments, like where galaxies are near each other. In regards to this is something we call stripping or strangulation. Some people will use all sorts of fancy words to describe this, but it essentially is a mechanism of removing gas and dust from galaxies to stop them forming stars. Instead of star formations decreasing over time, you need to get rid of the stuff that makes stars to do that. And this is one of those mechanisms. And so from this, we're seeing here some really nice, again, tidal structures, but this is streams of gas and dust being thrown out of these galaxies as they pass by each other, which is pretty cool.
I think there's another thing that I noticed. I think it's on the galaxy to the left, where the spiral arms, there's like a lot of stuff going on that I think the Hubble image did not capture. And to me, it seems this is dust obscured star formation in the spiral arms. So if we compare these 2 images, side by side, as Stephen's doing for us here, you can see that, there are some star forming regions in the spirals. Well, we live in a spiral as well, so that's where a lot of the star formation happens in a spiral galaxy. But with the infrared image that Webb has provided, we can actually see these regions glow up in infrared light. Which I think to me is so cool, because you couldn't see these sort of details before Webb actually took this image. And with this resolution and clarity as well, because we've had space-based infrared observatories before, but none of them had the resolution to actually match Hubble's resolution.
And I think this is the image you're talking about here.
Yes, that's the one. I think the one on the left. I'm not sure if the screen is doing it justice, but if people go and look at this image and try and put them side by side with Hubble, you can really see that there are regions in the spiral arms that are lighting up, which is absolutely fantastic.
And I think the other thing about this image as well, because they're such high resolution, it pays to go to the sites, zoom in and click on expand, because you don't realize just how many pixels are in these images, just quite how high resolution they are until you do that, which I guess is where other people can see so far.
I can add just one quick other thing is if you're doing a side-by-side comparison of the Webb image with the Hubble image, is pay particular attention to the very small fake things that are all around the edges of the images, and particularly how many more there are in the Webb images compared to Hubble will show that the increased sensitivity of the telescopes allowing us to account these very small, very fake things in this universe.
Yeah, and I just want to point us back to that Southern Ring Nebula as well, because not only do we have an image of this beautiful 3-color image of the nebula in one wavelength, we've got it in another one. So we have 2 images from the same telescope at very, very different wavelengths. So one's done in the near infrared with an instrument called NIRCam, and one is done in the mid infrared. So this is much, much further into the red. And this is done with MIRI, the mid-infrared instrument, and the UK has a humongous involvement in the development and operations of this instrument. And you can see from those 2 images that they've released to you, just the differences between these 2 wavelengths from the same telescope. And it's a really, really beautiful showcase of how dynamic we're going to learn about the universe, because not only are we going to see each of these aspects in just one physical size where we can see through the dust, we're going to see it in 2, 3, 4, many different aspects, because this telescope stretches all the way from the optical out into the mid-infrared. So we've got this humongous laboratory to learn about different aspects and different areas of the universe.
So we've got some questions here on YouTube. We've got one that says, what is the range of Z values for the galaxies in this image? About how far back are we looking?
So that's
I'm assuming-
referring to the Z, the redshift of the galaxies, and thereby how far away that you would like to take that.
Exactly, yeah. I suspect that's going to be something that a lot of people are going to be arguing very quickly. It's probably going to be one of the first things that people are doing is trying to figure out what's the highest redshift thing that's in these images. We've already had spectroscopic confirmation of a couple of these things being at redshift 6 and redshift 8 and redshift. Hubble went up to redshift 10, redshift 11.
Tell us how far that is, how far back in time.
Well,
How
redshift
long's the
8
light picture?
Well, redshift 8 was the 13.1 billion year figure that I gave just before. People are thinking that we'll probably find things in these web images that are, we're pretty confident that we'll find things at redshift 12 to 14. Going beyond that, I think Steve might have to say about that.
What is the redshift of 14?
Redshift 14, oh God, what is that?
That's a big one.
It's less than 500 million years after the Big Bang.
Right.
So that's around 4% is current age, 3%.
So we're looking back from 96% of the
Yeah,
age of the universe.
exactly. So I think the number that people are going to be is essentially going to be erased. You'll see loads of papers and publications talking about all claiming to break the record, and then within a couple of days there'll be another paper come out saying we've broken the record. This is the highest one. But yeah, it's going to be a very hot topic for the next 3 months, I think, because there's not only this image right here, but there's a number of other deep fields that Weber's going to be taking, or has already taken, that's going to be released on Thursday, that people are going to be diving into as soon as possible.
And does that include the three of you?
Oh, yes.
I'm just
Let's just say that when this image got released, I had the Hubble images downloaded within about 20 minutes. I was already looking at them. It's very exciting.
I'm just going to give some more numbers for what Nathan was just saying, because I've just looked them up on my computer, my parameter. So redshift 14, which I think is kind of one of our realistic limits, not necessarily for this image, but at least for the first few weeks of Webb, that corresponds to only 300 million years after the Big Bang, so less than 3% of the age of the universe. In terms of a distance, that is almost 34 billion light years. Now that may seem a bit confusing given that the universe has been around about 14 billion years, but the reason why we can have a bigger distance is because during that time that this light has been traveling, the universe has continued to expand and get bigger and bigger and bigger. So this really is kind of a, almost 34 billion light years. Now, the moon is a light second away, right? To give that some kind of perspective there, right? So this is, billions, hundreds of billions, thousands of billions, trillions of times further away. Some of these numbers are just, I don't want to say the word astronomical because that's obvious, but they're just almost beyond our comprehension.
Thank you. Okay, good. I think there's a couple of others.
Yeah, so we've got a couple more here. We've got one question saying, is it like the same dust we get here? I think that was in reference to the opaque material that you were talking about, Hannah.
So is the dust that you find in space the same as the fluff that gathers under our bed? That's how we're doing that.
That's an interesting question. And actually, in some regards, yes, because a lot of this dust is a magnesium silicate. So it's actually more like the sand that you get on beaches, but much, much finer. And imagine, you're walking into the house, you've picked up some dust, some gravel, some dirt on your shoes. Contained within that dirt that is going to pile up in the corners of your room is this magnesium silicate material, which is this obscuring material that we're seeing in some of these nebulae. So yes, throughout the universe, there are grains of sand, just like we have on our beaches, that are getting ready to form stars and planets.
One more. Will every deep field show lensing distortions such as these? How common are they in deep fields?
So the question is from someone online, will every deep field show the kind of lensing distortions, those beautiful arcs that we see? And how common are these? Perhaps actually you could say what they are as well, and why they're say that, Steve.
Sure. The answer is not all deep fields will have. So what we're seeing in this image behind us is a relatively nearby group of galaxies called a cluster of galaxies. So these clusters often contain hundreds of thousands of individual galaxies. Because that's a really, really huge concentration of mass. Now, what Albert Einstein predicted, a little bit more than 100 years ago, is that this mass should distort the light from things behind. And that's exactly what we're seeing. So these arcs, which you might be able to see around the center of the image, these are galaxies who lie behind this relatively nearby cluster, and their light has been distorted and magnified by this cluster. Now, this is really, really useful for scientists like the three of us, because it allows us to essentially see more distant objects in more detail. So this really allows us to, look even further back in time by taking advantage of these essentially natural telescopes. Now, there are lots of these clusters out there in the universe. There's maybe a few hundred that we could really use for this experiment, but actually analyzing these images is really, really challenging. So in addition to these types of clusters, we also do kind of the more traditional blind fields, where we pick as empty a patch of sky as possible, and we take a really, really long integration. And so this was first done with the Hubble Deep Field all the way back in the middle of the 1990s. And this tiny fraction of the sky, really that first field was, a few grains of sand held at arm's length. That tiny fraction of the sky, when we looked really closely, contained thousands of galaxies stretching across the history of the universe. And so what we're seeing behind us is just one of these first deep fields that we're going to see. And in fact, actually by the end of the week, I think we're all really excited that actually there's about 4 or 5 other deep fields that we're going to be able to analyze. Maybe on Friday after the conference, after we've left now, we'll be downloading them all and hopefully finding some of these really, really exciting galaxies. But I'm involved, and the rest of us here are involved in programs that are going to collect data, over the next year and beyond. And so we've got a really super deep field, which we're going to get around Christmas time. So that's going to be another nice Christmas present for us. This is a program called NG Deep, and that's going to be even deeper than this. In fact, a lot deeper than this. And then we've got another program coming out over this next week called SEERS. This is the Cosmic Evolution Early Release Science Survey. And again, this is all just the tip of the iceberg that we're seeing.
Yeah, and it's not just about the galaxies. We're going to get even more exoplanets as well, and
A sense of rivalry.
just a little bit. And I'm going to pass on to Evie, who's leading one of our early release science teams for that.
Yeah, I can completely say something about that. So the early release science team on the transgender exoplanet community has a couple of observations coming. Actually, the first one was taken on Sunday at Actius. So we'll get the data down in the next week. My data is supposed to come on Monday. Reschedule it. But yeah, so I'll be working on James Webb data next week.
So
look out for that.
it sounds as though Stephen will be doing this work on the train home on Friday, and you'll be getting the weekend off and looking at it on
Correct.
which there are worse weekends to have, I guess.
I just wanted to say that all of these programs, these early release science programs we're talking about, they're international community efforts, and none of the science that we're seeing behind us is an individual coming from this. This is a huge group, a massive scientific community, and the beautiful thing about this new telescope is the ability to bring so many people together to work on these data sets and learn so much more from each other as well. So it's a really exciting opportunity to just work with scientists from across the planet.
I think that's a fantastic point to make. I think I'm looking at my colleagues. So, Gertrude, I'll have to accept that they're just in the background to fielding questions online. So I know we have a few journalists on the call registered. So I'm going to put this out to them. If they're still watching, they're very welcome to ask questions. So go ahead, and I'll take the question, Gertrude, where you think we'll be delighted to hear from you. So, Gertrude, what's the next one?
So a couple more questions here. One is, when will we get the first images of planets?
That is a very good question. When are we going to get the first images of planets? Hannah looks raring to go on this one.
I love planets. Planets are the best.
Planets are great. We all like planets and galaxies.
So there are 2 different ways that we can get planet planetary information from JWST. One is what we've already seen today, the spectra of the atmosphere of a transiting planet, a planet that passes in front of its star. But JWST is also equipped with something called a coronagraph. This is placing a physical mask in front of the stars so that it blocks out the star's light. We don't want to see the stars. So that allows us to see the planets glowing. And these planets are very, very young, so they're very, very hot because of that. So hot from their formation. So just after they've formed, they are still contracting under gravity and they're releasing heat as they're doing this. And by blocking out the star's light, we can measure the heat from those planets, the light from those planets. And JWST is in infrared, which is heat. And that means that we get a really great view of it. So the first direct images of planets are going to come from this method, this coronagraph method. And there is an early release science program which is being led by Sasha Hinckley at the University of Exeter and Beth Villa at the University of Edinburgh. So it's a beautiful UK-led team there that are going to be getting the first direct image pictures of some exoplanets. So hopefully very, very soon we'll start seeing those.
That was going to be my next question, is when can we expect to see those images?
I know that they're scheduled for them in the next couple of weeks. A lot of this early release science is planned as soon as possible, basically. It's early release science. The aim of these programs was selected for the telescope to do a range of different scientific investigations, like our deep field investigations, looking at galaxies, like our transiting planets, looking at spectra, and like the direct imaging ones, looking at directly imaged planets with these chronographs. So they should all be coming out as soon as possible, but we do need time to analyze these data. There's huge amounts of information in there that we have to pick apart and understand. So hopefully very, very soon.
Just to add, it's actually not just planets outside the solar system that we can observe.
That's true.
Where we can also observe, the planets in the outer solar system. So it can't look beyond the Earth, it can look inside the Earth's orbit, but it can look to, for example, the gas giants, the ice giants, and even smaller bodies. I think exactly that. I think it's looking at Jupiter on Thursday for one of our colleagues at the University of Leicester.
It is.
Lee Fletcher's program, I think. So he's actually on holiday right now. So if you're watching, Lee, I hope you're excited. We're going to get you updated really soon as well. So I think Lee and his collaborators across the world will be looking at Jupiter in a completely different way. And although we can send probes to Jupiter, right, give us really clear pictures, what those probes often can't do is track how Jupiter changes over time or observe it in infrared. So even though we can send probes to places like that now, there is still huge value in observing even things like Jupiter, which you can see with your own eyes, maybe not at the moment.
Early morning.
Early morning, thank you, Robert. There's still really great value in looking at things like Jupiter and the ice giants and Saturn with telescopes like well.
And I think we saw that with Hubble as well, because you saw great images of Mars and Jupiter and outbats, and there's only space probes aren't always there. I mean, maybe in Mars that's almost true because you often have roads on the surface, but the ability to monitor the distant world as telescopes get better, must be dependent. Must be really cool.
Yeah, we can expect in the next decade or so a mission to one of our ice giants, Uranus, most likely. It's only through observations from the Hubble Space Telescope and upcoming observations from the James Webb Space Telescope, along with some really great ground-based campaigns, that we can plan that mission. We can design and understand what it is that we need to do so that we can learn more about this very alien planet in our own backyard. So there's a huge amount that these telescopes allow us to do to plan for more in situ missions where we can throw something at it. But for these exoplanets, we're not going to lob anything at them for a long time. So this is really our way of getting in touch with these alien worlds and trying to understand what they're like.
And when she says getting in touch with the alien world, it's the caveat.
Yeah, there's a caveat there. Yes, it's a very, very distant kind of voyeuristic version of that.
Long distance relationship. Okay, thank you, Gertie. I think there's another question. So.
Yeah. So this one asks, how large or small of an area of the sky do you expect will be covered by deep field photographs from the JWST by the end of this year? Will it be focused on one area or multiple?
I'll ask that again. So the question is, how large or small an area of the sky will be covered by these deep field images, and will there be, a single deep field or multiple ones, and what can we expect? And I'm guessing not so large area of the whole sky that aren't the one happy to be closed.
I will correct you. So it's actually, well, it's a significant area of the sky. So there are several different programs that are going to look at, different patches of the sky. But there are some programs which are going to go quite wide. So the widest program is approaching almost a square degree, so about 4 times the size of the full moon. And the reason why we want to do that is to find rare objects, right? But at the other end of the scale, the program that's going to be doing that is going to start doing data again around Christmas times. This is something called Cosmos Web. So it's this big field. And so we use that to find rare objects. But at the other end of the scale, we're going to do these really, really deep fields where you don't really move the telescope, you just stare at one direction for a huge period of time. And that allows you to see the really faint things. But the problem with doing that is you're only looking at a really small fraction of the sky each time, right? And so you might be looking at a privileged part of the universe and not kind of the average area. So we've, for a long time, done what we kind of call a wedding cake of surveys. So you have kind of shallow tier at the bottom, so big wide tier like Cosmos Web, and then you'll work your way up to these really, really deep fields, like the image that we still there behind me, or like the Hubble deep field. And really, by combining all of these together, we really, understand our universe in more detail.
I think the wedding cake analogy is going to get used. Something about a wedding anniversary type of
So kind of to go through all the podcast, in terms of the numbers of these, we're probably going to have by Christmas, it's going to be numbered in the tens of deep fields. And some of these, as we mentioned before, some of these will be based on, well, centered on clusters, such as the one we've got behind us, using them as a lens. And some of them are going to be what we call either blind or blank fields, where we're trying to make sure there's nothing in the way. But there's going to be, like you said, a wide variety of this wedding cake approach that allows us to capture the rare things on large scales and also look for the very faint, distant things on small scales. So I lost my train of thought there. There was something else I was supposed to add, but I apologize. But in terms of the number of areas, it's going to be numbers in the tens. And the reason why we want to look at different patches of sky rather than just all of these aren't clustered all within a small patch, they're all over the whole observable sky, is again for that same reason that Steve just mentioned with regards to we want to make sure we're not looking at very privileged areas. We don't want to accidentally look at an area of space, it just has to be a bit empty in the west or a bit overabundant in galaxies in the west. We want to get an idea of what the universe looks like in all directions, so make sure we're not making a biased observation.
Yeah, of course.
Yeah, I think one important thing to keep in mind is that James Webb is not really a survey telescope, because compared to other telescopes that we have on the ground, the field of view is actually quite small. So you can't really, map large portions of the sky and basically create things that we call all sky maps. Like you see from, slow digital sky survey or pan-stars. And that's something that Euclid and Roman telescopes will actually try and do. So James Webb is more of like a targeted telescope, but since the field of view is small, but the sensitivity is ultra high. So the kind of science that really what motivates James Webb is to do deep fields. Well, of course, you still need certain larger areas, as Steve mentioned, because you want the rarer objects. But it's by no means going to cover all of the sky, for example. It's only going to be limited to some of these sort of famous deep fields that also be studied in the Hubble. And so that, I think, is important to keep in mind, that it's not actually doing a survey of the entire sky, but only certain patches in the sky where you know where things are.
We've got one more. Would the JWST be useful in refining our yardsticks by taking more precise parallax measurements, or are there better things for it to be doing?
I'll repeat this question for laughing for reasons. So would the JWST be used to do things like refine the yardsticks, which are astronomy thought of as the way we measure distances across the universe, including things like the parallax, which I'll perhaps ask one to explain. And alternatively, are there better things for it to be doing? You're free to give your own opinion. So I guess you would like to take that.
That's not, yeah. I think arguably, like Gaia, for example, is the survey to really nail down parallax measurements, because again, I think it comes down to numbers over numbers and coverage area, because James Webb can't really sort of constrain properties from a large number of sources spread across our own galaxy, for example. And to refine distance measurements, I think using parallaxes, for example, you need tons and tons of stars to actually constrain these parameters. Right? And that, I think, Gaia, nothing can be Gaia at the moment, which is also L2, so it's actually James Webb's neighbor in L2.
And presumably in Gaia, which essentially, well, the biggest part of its mission was to map the galaxy, measure the vast number of stars in the galaxy. Presumably, scientists using James Webb will be drawing on that. Some of them will.
Absolutely, yeah, because Gaia is looking at all the parts of the galaxy, and it's finding these amazing, star-forming regions, or what we call OB associations of like these very massive stars that formed very recently. But Gaia, it has an imager and a spectrometer, but it's not really designed to do that. It's mostly designed to measure the proper motions of the stars in the galaxy. And for things like James Webb, to follow up on important pre-discoveries made by Gaia is going to be absolutely fantastic. Because you can really peer down into that region, look at the individual components in these star-forming regions, and get a lot more physics out of it. So I think, yeah, like I don't think James Webb is a parallax telescope or a parallax instrument, but it does have a lot of value in sort of adding to what already some of the satellites are doing.
Yeah, and just to add to that, I mean, that's entirely true, but parallax is just the bottom of the distance ladder. So we can't really use the parallax technique. So this is a technique where we use the apparent shift in the position of stars or other objects over half a year to kind of infer how far they're away. In fact, actually parallax is one of the ways that we have depth perception. So our eyes, we've got two of them, and so we're actually seeing objects in different ways from each of our eyes, and our brains interpret that to actually give us some idea of the depth or the distance to an object. But this really is just the bottom of the ladder. So some of the things above the ladder are things like looking at individual stars, particularly stars like second variables in distant galaxies, and your Webb's resolution and just sensitivity will allow us to push that bit of the distance scale further. But I really like supernovae. I like things exploding. And although Webb isn't really designed to find supernovae, because to do that you need to look at the same patch of sky again and again. When we do find supernovae with other telescopes, like the Vera Rubin telescope, which is going to start collecting data over the next couple of years, Webb will allow us to look at those supernovae in real detail and really understand them. And so it does play its part in this whole kind of measuring the distances to objects, allowing us to really, ultimately understand what our universe contains, how it changes over time, and how it will change in the future.
Okay, I think was looking to say there's a question from one of the journalists.
Yeah, we have a question from Daniel Lawler from AFP News Agency, and they ask, what would you describe as the biggest surprises from today's Webb release?
So I'll put that, I'll repeat it for the benefit.
Or releases.
This is Daniel Lawler from Agence France Press, and he's asking, what would you describe as the biggest surprises from what you've seen so far in today's releases, and the one, I guess, the last slide as well.
Well, one of the things that we mentioned earlier was that alongside the release of this image, they announced they take some spectra of galaxies, which was something I don't think any of us expected. We thought we were going to get the image, and that was it. So that was a surprise purely from we weren't expecting that to be done side of thing. In terms of surprise from the science point of view, is particularly looking at this cluster image and comparing it to the image we had before from Hubble, was how many objects in the Webb image are not present in the Hubble image at all. And so within minutes of the image going up, my phone was going nuts with people sending texts, emails, all sorts of things like, have you seen this? Have you seen this? It's like all of these things are in this image that aren't in the Hubble image. And these are the really red things. They're keeping from James Webb standards, they're very red, so quite easily infrared. To use point test here. So the particularly red looking things in this image is red even for Webb, but then for Hubble it doesn't go that red. And these things should be just completely invisible. So that was a big surprise for us, which is how many of these things just appeared in the images.
A light note, what was surprising for me was how hard it is to coordinate international response to a large astronomical
That's a
event.
very fair point.
So that was, it is challenging, yeah, we've all been through that, and it's a surprise and also reassuring that NASA is basically saying the same measures that we all do every day.
I think you'd be utopian not to really. It's a really tough call. But I mean, the nice thing is to know that, although this is the UK meeting, there are people from, I think, 36 countries here, but nonetheless, even as a UK meeting, that there is a sufficient vibrant JWST community. So many people here are looking forward to getting data from the telescope, or indeed, in many cases, have a hand in its construction. It's have the oversight of it from the very start.
Yeah, and I think there's one thing that every single person out there can appreciate from these images. It's just the structure, beauty in absolutely all of them, in many different ways. I mean, just look at that nebula image. It is unbelievably beautiful. And that I just don't think you can, it doesn't need selling. It's right there. You can just see it with your own eyes just how amazing that is.
What's your biggest surprise so far?
I mean, the pictures are amazing. I particularly like the one with the two. Just seeing how the images is exceptional in JWST. But about I think as a PhD student who does the work on transmission spectrum, I appreciate so much the work that goes behind actually getting the spectra and the data, doing all the reduction. The instrument they used in the picture is this mirrors, which is particularly hard because it spreads the spectrum of the picture, just multiple orders in it. So I'm really appreciative of the effort that went into just making the spectrum and seeing the water and water vapor there. So I'm super excited to also see what we get of instruments there. So yeah, that's for me.
And Stephen, you just asked before, what's your biggest surprise so far?
Just how overwhelming it is. So just looking at that first image last night, and I know that's just the tip of the iceberg, and it's just so rich, just so full of science ready to do. Right, I just want to go download it and actually start playing around with it, start trying to understand. But again, I think at some point we should all answer which is our favourite image, because I'm staring at one which is probably the most unrelated to my science. I'm just astounded by the beauty of it, right? The great thing about astronomy is that even if you don't really care about science, you can hopefully appreciate the beauty of our universe. And I remember 5 or 6 years ago when I was talking to various people about Webb, they were kind of saying to me, oh, but it's infrared, it won't take as nice pictures as Hubble, will it? And I was like, no, it will take much better pictures, it's beautiful. I won't mention the name of that particular astronomer who I had that conversation with. But just looking at this stunning image, I mean, I grew up remembering Pillars of Creation, and just I remember being blown away by that, and just being blown away again by this one, 20 years later.
I think what's nice as well is that when Hubble watched, those are the super-memory, and I realise that in some cases, as anybody that possibly wasn't born when Hubble watched. But actually, the big thing with that was, of course, the mirror was the wrong shape. So they had to fix spherical aberration. So although it was used in a compromised way for a couple of years before the service commission was struggling to fix it, actually it was notorious at that time for being, well, taxpayers paying all this money, putting this thing in space, and it didn't quite work. Well, I think the great thing, fortunately for all of us actually, is that JWST has been so brilliant, that it's worked well so far. Touch whatever piece of wood or superstition you've got, it's worked pretty well for us as astronomers.
Yeah, and that comes down to the design. Each of these 18 individual mirrors can be moved independent of each other, and they spent over a month aligning these mirrors to get that beautiful crisp star that you've got there, those spikes. That is meticulous planning and time. It took a day or so to move just one mirror, and tiny little reaction motors you had to use in turn in sequence. So that's no coincidence. That is design, and that is just a testament to the humongous amount of people and the hard work that went into this telescope.
I'm gonna, please feel free to chip in as well. I think we've got one more question on YouTube, is that right? And then we should bring it to a close, I guess.
Yeah, sorry. Just expanding on that, one of the things you mentioned at the very beginning was how we felt when we first saw the images. And everyone was being excited, and it was Christmas. And for me, it was one of relief, because we've had months of our colleagues who have done the calibrations and things saying, oh, it's amazing, everything's beautiful, it's all working, it's fine. But when this is probably going to form a significant part of my career, and with yourself and things, there's still a huge amount of nerves around it. And it's like, oh, please work, please work. And when you see the image for the first time, oh my God. Oh, yes, I still have a job.
That's a very fair point. I mean, you know, when it launched, we prepared two statements. The RAS, we obviously prepared the congratulations statement. We also prepared the, okay, this is the green thing we put out. And probably not many of us do interviews on the back of this because we knew the risks. So yeah, it's absolutely, I think it's fantastic. But I will now take, I think, one last question, and then we can bring to the close, because I know people to escape actually out of it. So, Virgie.
It's a nice one to finish on. What is on your JWST wish list? What would you like to see imaged by?
So the question is, what's on your JWST wish list? What would you like to see imaged? I'm going to give each of you a few seconds just to come up with an answer to that. So, or to answer that, go for it.
So scientifically, obviously, the deepest deep field we could possibly do. So take one little patch of sky and just stare, because not only will we find, you know, some of the most distant objects in the universe, we might find things that we haven't even anticipated yet, and that's really, really exciting. So there are a whole lot of things that we know we're going to be able to answer with Webb, but I think the most exciting things are the, you know, to quote Donald Rumsfeld, maybe the unknown unknowns. But at the same time, I'm sat staring at this image of the nebula, and I want to see the pillars of creation. That iconic image from Hubble that Hubble has returned to a few times. I want to see Webb's version of that. It's beautiful.
Great. Okay, Nathan.
I mean, pretty similar to Steve from a scientific point of view. I mentioned earlier that like sort of realistic sort of redshift range, and we were talking about the probably pushing to redshift 14 or so. And my scientific interest is trying to do the deepest image we possibly can, stare at one patch of sky as long as we can, and see if we can go 14, 16, 18. When did the first stars form, and see the very first stars that formed?
Yeah, I think I'll tell you what my scientific wish list is. Maybe what we can try and find is the first generation of stars in a very distant galaxy. And that is where the spectra would play a massive role. Because if we find, you know, stellar populations that only have hydrogen and helium, that, for example, would be a perfect sort of perfect representation of a galaxy that does not have any chemical elements. And yeah, that for me would be groundbreaking, because we've never found this first generation of population 3 stars before, and Webb can do that. If we find that would be the holy grail, I think.
And I'm guessing that Hannah or Evie can add some different answers.
Not surprisingly, it's plus. No, actually, pillars of creation. I was kind of like thinking that that's what they were going for before they announced the targets. I was kind of looking for it, so I really want to see it. So I'm review on that one. But also, like, I'm really looking forward to see like direct image planets. There's just something about actually seeing the planet. Like, as much as I love transmission spectroscopy and also emission, direct image planets has just, I don't know, just something to I don't know. Whatever, Johanna.
I'm greedy. I want to see not just one spectrum of an exoplanet. I want to see a whole load, and I want to see them across all masses, right down to that terrestrial world, and measuring for the first time definitively that these rocky planets that we discovered out there have an atmosphere around them. So to get there, we've got some work to do, but I think we're up for it.
That's a very fine note to end there. I think that Stephen looks like he wants to chip in with one very short
Always,
point. I'm going to give you a
always.
very short point.
Just to cover all the science, I do really want to see Saturn and Jupiter as a viewfinder as well.
You're into matching, the ice giants.
Okay.
Ice giants.
There we go. Some debate on this. I mean, I guess the nice thing is these are things you can see for yourself with your eye and then get to compare it with what the telescope will show us. Okay. I think that's a fantastic point to bring it to an end. And I know that some of you are going to use other outlets. So we'll leave it there. I hope that people watching us enjoyed this. Do feel free to get in touch with us. You can tweet us at @AstroSoc, or you can tag the conference at come with the hashtag something like now Warwick 2022. But there are hundreds of astronomers here for the next 3 days. So do tag the conference, tag us in the RAS, and we'll pass on the questions. I'm sure people will be very interested in seeing the conversations and continues. So with that, these things are always very abrupt in the way they come to an end. But thank you very much for watching.
Thank you.
Enjoyed it as much as we have.